Welcome to this lesson. I'm teacher Katimbo Richard, teaching mathematics P5. Today I've come with patterns and sequences in this P5 class, which work will be found on page 78 all the way to 99. That is, if you followed this video properly, you would be able to answer all the activities for the said pages of 78 all the way to page 99 of that workbook of our P5 term 1, and you will be successful. Like I said, we are looking at patterns and sequences. That's P5 term 1. We shall start with the types of numbers. In your P4, you must have looked at some types of numbers, and now we are continuing with some other types, including some we found in P4. So we shall start with the prime numbers. What is a prime number? That's the question. One must know that a prime number is a number with only two factors, that is 1 and itself. A prime number is a number with only two factors, 1 and itself. You must know a factor is a divisor. For example, when I say 3 times 1 and I get 3, then those numbers are multiplied to get that 3 is factors. So factors of 3 are 1 and 3, 1 and 3, 1 and 3. And a number that's got only two factors is called a prime number. When we go and get asked for the factors of 4, you must know the tables under which 4 is an answer. You can go table 1, table 2, and table 4. So, of course, 1 times 4, you get a 4. 2 times 2, you get a 4. And 4 times 1, you get a 4. So the factors of 4, or the tables that lead to 4, are table 1, table 2, and table 4. Meaning, they are the only numbers which can divide 4 without leaving a remainder. For 4 divided by 1, you get a 4. Then 4 divided by 2, you get a 2. And 4 divided by 4, you get a 1. So that's got 3 factors. Now, that one has got more than 2 factors is not called a prime number, but is called a composite number. A composite number is a number with more than 2 factors. And the prime number is a number with only 2 factors. So we're looking at prime numbers here. So prime numbers, So numbers with only 2 factors are 2, 3, 5, 7, 11, 13, 17, 19, and so on. So they have got only 2 tables, table 1 and themselves. That is where you can find them. So factors of 2 are 1, 2. Factors of 3, 1, 3. 1, 5. That's for 5. Factors of 7, 1, 7. Factors of 11, 1, 11. Factors of 13, 1, 13. Factors of 17, that is 1, 17. Factors of 19, 1 and 19. We don't have any other number that can divide them without leaving the remainder. So you cannot divide a number like 13 by any other number apart from 13 and 1. So, get no remainder. So therefore, the factors of 13 are 1 and itself. So, a prime number is that number has got only 2 factors, 1 and itself, as opposed to composite numbers. So we go to the next type of numbers, which is composite numbers. What is a composite number? A composite number is that number has got more than 2 factors. It is the opposite of prime numbers. So numbers with more than 2 factors are said to be composite numbers. And numbers with only 2 factors are prime numbers. Numbers with more than 2 factors are called composite numbers. So any number that's not prime is a composite. Remember number one does not get involved in any of the two. Is not a prime number and neither is it a composite number. So that one is not. Why? It does not have 2 factors. It has got only 1 factor. Whereas here we must have 2 factors. Whereas in composite numbers we must have more than 2. So 1 is not among these 2. It's neither prime nor is it a composite number. Be careful about what we are dealing with. So the numbers given here have got more than 2 factors. That is why they are called composite numbers. So composite numbers are those numbers that have got more than 2 factors. If 2 is a prime and 3 is a prime, the number skipped here is a composite. That's why the first composite number is a 4. The first composite number is a 4. I say exclude 1 in any of the 2 categories. 1 must not appear anywhere here among the prime and the composite numbers because it has got only 1 factor. Prime numbers must have at least 2. So it must have only 2. Only 2 factors. Only 2 factors. So then composite numbers must have 3 factors. So 4 appears in 3 tables. Table 1, table 2, and table 4. So that is why it is having 3 factors, 1, 2, and 4. Then table 6 has got table 1, table 2, table 3, and table 6. It has got 4 factors. So meaning, when you say 1 times 6, you get 6. 2 times 3, you get 6. 3 times 2, you also get a 6. And then 6 is so 6 times 1, you get a 6. And so it has got 4 factors. That is 1, 2, 3, 6. 1, 2, 3, 6. So anything with more than 2 factors qualifies to be a composite number. Then we go here after 6, 7 is a prime. It has got 2 factors. Now 8, 9, and 10 are missing here. That's why they're here. 8, 9, and 10. 8, 9, and 10. 8, 9, and 10. Let us see the factors of 8. Tables under which 8 is an answer is table 1, table 2, table 4, and table 8. So it has got 4 factors. That is 1, 2, 4, and 8. 1 times 8, you get 8. 2 times 4, you get 8. 4 times 2, you get 8. And 8 times 1, you get 8. So therefore, it is a composite number because it has got more than 2 factors. It has 4 of them. That is 1, 2, 4, and 8. Then 9 appears in table 1, 3, and 9. 1, 3, and 9. So it has got 3 factors. It is a composite number. Then 10 it appears in table 1, table 2, table 5, and table 10. So it's got 4 factors. That is 1, 2, 5, and 10. Then 12. Because 11 is among prime, then what is missing here? 12. Between 11 and 13, it is a 12. 12 is a composite number. It has got like 4 or 5. Let us see how many factors it has. That's table 1, table 2, table 3, table 4, 6, and 12. It has got 6 of them. 6 factors. That is 1, 2, 3, 4, 6, and 12. It has got 6 factors. So, therefore, any number with more than 2 factors is a composite number. We go to 14. 14, now that 13 is a prime, and now 14, 15, 16 are missing here. They are the ones here, 14, 15, and 16. Before we go to 17, that side. 17 is the prime, so it cannot be this side. So 14 has got more than 2 factors. It has got 1, it has got 7, 1, 2, 7, and 14. So that's got 4 factors. 1, 2, 7, 14. 1 times 14, you get 14. 2 times 7, you get 14. Then you got 7, so 7 times 2, the 14, and then 14 times 1. So that's got 1, 2, 7, 14. So that's got 4 factors. Then 15. 15 is also a prime number. Why? It has got more than 2 factors. So it has got 1, 3, 5, and 15. 4 of them. 1, 3, 5, and 15. Here, knowledge of the tables is very important. If you don't know the tables, please use this lockdown, that is school lockdown, for you to recite the tables, because you don't know the factors. The numbers that can multiply to get 15 are the factors. 1 times 15, you get 15. 3 times 5, you get 15. Likewise, 5 times 3, you get 15. Then finally, 15 times 1, you get 15. So it has got 4 factors. That is 1, 3, 5, and 15. Then 16 also is under the composite numbers, because it's having more than 2 factors. That is, it has got 1, table 2, it has got table 4, it has got table 8, as well as 16 itself. So it has got 5 factors. That is 1 times 16 is 16. 2 times 8, you get 16. As you move, after 2 you go 4 times 4, you get 16. Then 8 times 2, you get that's 16, and 16 times 1. So that's got 5 factors. That's 1, 2, 4, 8, and 16, and so on. So composite numbers are chosen like that. So a number is said to be prime if it has got only 2 factors, 1 and itself. So like 13 has got 1 and 13. 2 has got 1 and 2. Just like that. And then composite numbers are those that have got more than 2 factors, meaning from 3 factors and above. Those are said to be composite numbers. We shall see how applicable they will be the other side if we continue together. Please continue watching as we look at the third type of numbers, which is odd numbers. The question is, what is an odd number? An odd number is that number which, when divided by 2, there is a remainder. It is a number which, when divided by 2, 1 leaves a remainder. Or simply, it's a number that's not exactly divisible by 2. An odd number is a number that's not exactly divisible by 2. Or, you say, it's a number which, when divided by 2, 1 attains a remainder, or 1 gets a remainder. And now the examples, odd numbers are, that is 1, 3, 5, 7, 9, 11, 13, 15, 17, and so on. So wherever you divide any of these by 2, you get a remainder. That is 1 divided by 2. Of course, 1 remains undivided, everyone gets nothing. So 1 mango divided by 2. Without necessarily cutting this mango, everyone get a whole. So 1 mango, that is 1 mango divided by 2. No one gets, because that 1 is already 1 and no one can get a full. So everyone gets nothing and 1 remains undivided. 3 divided by 2, that's 2, remainder 1. 5 divided by 2, I said 3 divided by 2, that is 1, remainder 1. Then 5 divided by 2, 2, remainder 1. 7 divided by 2, that is 3, remainder 1. 9 divided by 2, that is 4, remainder 1. 11 divided by 2, that is 5, remainder 1. 13 divided by 2, that is 6, remainder 1. 15 divided by 2, each one gets 7, remainder 1. So you get a remainder for every time you divide. I said 3 divided by 2 is a 1, remainder 1. So each one gets 1 and is a remainder 1. So get to know when divided by 2, each leaves a remainder, meaning they are not exactly divisible by 2. In terms of a whole, there is a remainder that remains unshared. So therefore, those are odd numbers. Odd numbers are an opposite to even numbers. They are an opposite to even numbers. What is an even number? An even number is that is divisible by 2. A number divisible by 2 is said to be an even number. Or a number which when divided by 2 there is no remainder if you want. An even number is a number which when divided by 2, one gets no remainder. So like you see the examples here, 0, 2, 4, 6, 8, 10, 12, 14 and so on. So these are even numbers, meaning when I divide each by 2, people will get evenly and nothing remains. Everyone gets an equal share and nothing remains. For example, if I have nothing, that's 0. 0 first of all cannot be divided. Everyone gets nothing still. So that's even share. So 0 divided by 2, of course, cannot be divided, so no one gets. So everyone remains like they have been. Then we go 2 divided by 2, everyone gets 1, no remainder. 4 divided by 2, that's 2, no remainder. 6 divided by 2, 3, no remainder. 8 divided by 2, 4, no remainder. 10 divided by 2, 5, no remainder. 12 divided by 2, each gets 5, no remainder. And then 14 divided by 2, gets 7, no remainder. 16, you continue, 18, like that. Now, in terms of sequence, you will notice that odd and even numbers have got the same sequence. A sequence is like a flow, it's like a pattern. So, we look at the odd numbers about the sequence. So, now, what you call adding to the former number to get a new one, we see that 1 plus 2 gets 3, 3 plus 2 gets 5, plus 2, 7, plus 2, 9, plus 2, 11, plus 2, 13, plus 2, 15, plus 2, 17, plus 2, 19, plus 2, 21. So you go on adding 2, just like for even numbers. So 0 plus 2, you get 2, plus 2, 6, 4, plus 2, 6, plus 2, 8, plus 2, 10, plus 2, 12, plus 2, 14, plus 2, 16, plus 2, 18, plus 2, 20, plus 2, 22. That's why we say and so on, please. They are endless. We know the first, but don't know the last. So, all and even numbers have got a plus 2 sequence. That is what we're talking about, patterns and sequences. So, we go on adding 2, 2, 2, 2, 2, 2, 2, so it's like a song. Plus 2, plus 2, plus 2, 0 plus 2, 2 plus 2, 4 plus 2, 6 plus 2, 8 plus 2, 10 plus 2. It's like a song. So, that's what's called a sequence, like a rhythm of the flow of ideas. So, that is the sequence. So all the numbers and even numbers have got a plus 2 sequence, meaning go on adding 2 to get the next number in the sequence, because one day you'll bring such a number like, find the next number in the sequence, 0, 2, 4, 6, 10, 8, 10, 12, 14, dash. They will put a dash instead of and so on. So you just get 14 plus 2 and get 16 if you see they are even numbers. Just like here, you also add 2. So all and even numbers have got the same sequence of plus 2, 15 plus 2, if you have to get the next number, you get 17. And that is the way. So the way you do for all the numbers is the same way. 1 deals with even numbers. And in so doing, you will be a perfect person in that number. Now, we've so far looked at prime numbers, composite numbers, odd numbers, even. Now, we are looking at the 5th type of numbers, which is square numbers. What is a square number? A square number is the one, or is a number attained or got by multiplying the number by itself. Is a number got by multiplying the number by itself. Meaning, if I multiply 1 by 1, what I come up with is what's called a square. So 1 times 1 is a 1. That one I've got as the answer is called a square. Then the next square is 2 times 2, you get 4. So the square of 2 is a 4. The square of 2 is a 4. So 4 is the square and 2 is the square root. So opposite of square is square root. Root, like here, origin. I want to know your roots, meaning I want to know your origin. So square root, meaning the origin of the square. Where does 4 come as the square? It is a 2. So the square root of 4 is a 2. And the square of 2 is a 4. 2 times 2 is a 4. That outcome is the square, 4. But the root, where it came from 2 when it was squared. So 2 times 2 is a 4. 4 is the square, and the root of that square, called square root, is a 2. As we continue, the third square is 3 times 3 is a 9. So you get a 9. Then the fourth square, 4 times 4, 16. The fifth, 5 times 5, 25. The sixth, 6 times 6, 36. You must know tables. 7 times 7 is 49. 8 times 8, you go like that and get 81. 9 times 9, you get, so I'll say 8 times 8 is 64. 9 times 9, you get 81. Then 10 times 10, you get 100. So you must at least know the first 12 or the first dozen of squares. 11 times 11, you get 121. Then 12 times 12, you get 144. So the first 12 squares are 1, 4, you go 9, after 9, 16, after 16 you go 25, after 25 you go 36, after 36 you go 49, after 49 you go 64, after 64 we got 81, after 81 you get 100, that's the 10th square, then 121 is the 11th, then the 12th will be 144. So you must be knowing all that much. That's why the examples are 1, 4, 9, 16, 25, 36, and so on. These are the first 6 squares. 1 times 1 is 1. 2 times 2 is a 4. 3 times 3 is a 9. 4 times 4 is 16. 5 times 5 is 25. Then 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. Go like that. 9 times 9, 81. 10 times 10, as you write 100. 11 times 11, 121. 12 times 12, 144. As you continue like that. But at least you must know the first 12 squares. Please practice accordingly and then answer. So that's about square. So square numbers are got by multiplying a number by itself. Where you say 1 times 1 is equal to 1. That's the first square. 2 times 2 is equal to 4, the second square. 3 times 3 is equal to 9, that is the third square, like that. Then we go triangular numbers. Triangular numbers. How does one reach a triangular number? A triangular number is a number got by adding consecutive counting numbers. Consecutive counting numbers. The word consecutive means listing without omission, that style. So by adding the next counting number, flowing counting numbers. For example, if you are counting, you know 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you don't know the last one, but you know the first counting number is 1. So when those numbers are added repeatedly, with that flow, we get what is called a triangular number. We get a triangular number. For example, the first triangular number is 1, like the first counting number is 1. So we start with 1 and go on adding the next counting number. We add consecutive counting numbers. So that's why we've got plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8, plus 9. You go on adding like that. So 1 plus 2, you get 3. So this is a build up, like you see, from this one to that one. 1 plus 2, you get 3. 3 plus 3, you get 6. 6 plus 4, you get 10. 10 plus 5, you get 15. 15 plus 6, you get 21. 21 plus 7, you get 28. So you go on adding the next counting number. So that's why I've got 1 plus 2. Plus 3, plus 4, plus 5, plus 6. plus 7, plus 8, plus 9. You go on adding like that. They are endless. So this does show, please, the list is endless. You continue in that style. So in mathematics you learn how, not what the answer is. So the answer will be derived at if one has understood how we reach it. So we reach it in which way? By adding the next counting number. 1, 2, 3, 4, 5, 6, 7, 8. So we go on adding like that to get the next number in that sequence. Those are some of the numbers you need to know in our P5. And now we can use the same idea to do whatever we are going to do in our workbook. And as teacher continues to explain. Now we are going to look at what is called prime factorization. Prime factorization. Look at the word prime and then factor. So don't you see it? They are related. So this was related to this prime and the factors. So prime factorization. Prime factorization. That's why the first type of numbers I gave you was prime numbers, because I knew after thorough explanation here in terms of prime numbers or prime numbers, you'll be able to prime factorize. So the use of learning prime numbers was to prime factorize, because we have talked about the factors, we have talked about prime numbers, then we connect those two. That is prime factorization. So, like the word suggests, prime factorization is a way of expressing numbers in terms of their prime factors. Meaning, we are going to use prime numbers, which we have already learned today, to prime factorize. Like we are going to see, you must note these two carefully. A and B, note carefully. 1, we use a ladder or a prime factor tree to do what is called prime factorization. So in order to prime factorize, we can either use a ladder as a method or a prime factor tree, like we are going to see today, to do what is called prime factorization. And then 2, another thing you must note is the answer for a prime factorized number is expressed in 3 ways. 1, in multiplication form. 2, in power form. 3, in subscript form. In subscript form. All these are going to be looked at properly. You must know that the answer after prime factorization is expressed in any of the 3 ways. 1, multiplication form. 2, power form. 3, subscript form. And again, another thing one must note is that multiplication form can, on the other hand, be termed as product form. When I say A express 18 in terms of its prime factors, or as the product of its prime factors, it means do prime factorize and give the answer in multiplication form. So multiplication form is the same as product form. And then you must note that power form is also called index form. Is also called index form. When you see the word index, you just know that is a power. Or exponent form. When you hear exponent or index, they are meaning power form. Then subscript form is also called set notation. Set notation, like the word set is set notation form. So when you're asked to give your answer in set notation form, please give it in subscript form. Subscript form. And then we look at examples of the technical words teacher has already given to you now. Now, let's look at the general instructions, and here they are. Prime factorize the following and express your answer as instructed in the brackets. Prime factorize the following and express your answer as instructed in the brackets. Now, follow the instructions in brackets, then you answer. Now, number 1, prime factorize 18 and give your answer in multiplication form. Prime factorize 18 and give your answer in multiplication form. Remember, multiplication form is the same as product form, and this is the way we go about it. Like I said, we use a ladder or a prime factor tree to prime factorize this 18. So we are going to use a ladder or a prime factor tree. Now, teacher has chosen the use of a ladder. This is what's called a ladder method of prime factorization. In prime factorization, we use the division by the prime numbers. Like here, we want prime factorize. We want factors that are prime numbers that come out of a said number 18. Now, 18 is going to be divided by our prime numbers. Remember, they are numbers which have got only 2 factors, 1 and themselves. So, the prime numbers go in this line, 2, 3, 5, 7, 11, that order. So, then once we are going to use to prime factorize this 18. Now, as you see, the first prime number being 2. Ask yourself whether 18 is divisible by 2. If you know tables, then you will ably know that this 18 is divisible by 2. Now, 18 divided by 2, you get 9. You continue. Is 9 still divisible by 2? No. If you know tables, 9 is not a multiple. Now, we are going to the next prime number 3. Is 9 divisible by 3? Yes, you write it here. 9 divided by 3, you get 3. Good. Still 3. 3 divided by 3, you get 1. So you find out that the numbers we have used to divide here are all prime numbers. They are all prime numbers, meaning you have prime factorized. Now, the prime factorization is already done. The prime factorization is done. But now, they are saying, and give your answer in multiplication form. Now, the answer is this one. Therefore, our 18 equals 2 times 3 times 3. This is the answer. You underline 18 is equal to 2 times 3 times 3. This is what's called multiplication form or product form after prime factorizing. This is prime factorization. This is giving the answer in multiplication form. In so doing, you have got all the marks concerning that number. So that's the way we prime factorize. We use all the prime numbers to divide, but in order 2, 3, 5, 7, 11, 13. Please, in that order of prime numbers as you see them there. Then number 2 says prime factorize 40 and give your answer in power form. Prime factorize 40 and give your answer in power form. We say power form is the same as index form and it's the same as exponent form. So when they say index form, they will be meaning exponent form. So when you see the word index, the singular form of indices, they can as well say exponent form. So whether you say use exponents or indices or in index form, please use that power form. Now we are going to prime factorize before we give the answer. I said we use a ladder or a prime factor tree to prime factorize. Here we use the ladder to prime factorize. Now I've gone to what is called a prime factor tree, sometimes called just a factor tree. So a factor tree, this time round we shall not use a ruler to draw a ladder. We are going to use a prime factor tree. We use this symbol like this to divide. Here, put a number to divide by and the answer on the other side. Now, 40 divided by 2, you get 20. We are using a factor tree now. Later, we give the answer in power form. 40 divided by 2, you get 20. We draw this thing again. So 2 is still dividing that 20. So now 20 divided by 2, you get 10. 2 is still working. We draw like this. 10 divided by 2, you get 5. And the prime factor tree stops there. I've seen books that contain and say 5 divided by 5 and get 1. A prime factor tree, please, will never go as far as 1, like a ladder. Look at the ladder. When 3 divided by 3, you get 1. Whereas for a prime factor tree, please, that step where you reach 1 is left out. So don't add on here 5 divided by 5 and get 1. No, don't. So we say 40 divided by 2, you get 20. 20 divided by 2, you get 10. 10 divided by 2, you get 5. So the prime factors are 2, 2, 2, 5. 2, 2, 2, 5. 2, 2, 2, 5. They are all prime numbers, please. Meaning you have prime factorized fully. Now, give your answer. This is prime factorization using a factor tree. We have used a prime factor tree to prime factorize. Now we are going to express our answer in power form. Power form is the same as index form or exponent form. So what are the powers? So you count on the same digit used here. So I've got 2, 2, 2. So first power, second power, third power of 2. 2 to the power 1, 2 to the power 2, 2 to the power 3. If you want index, you say 2 index 1, 2 index 2, 2 index 3. That's why we've got 40 equals 2 index 3 times. We've got only 5. Only 1 5. So times 5 index 1. In so doing, you have primary 40 and given your answer in power form, or in exponent form, or in index form. And you underline that, nothing else. You get maximum marks in that regard. So I've so far looked at how to express our answer in mathematical form, like in example number 1. Now, we have as well looked at expressing our answer in power form, exponent form, as well as index form. Now, let's look at what number 3 example will present to us. If it's different, then we learn it. If the same, then we practice. So we go. Number 3 says, primarize 24 and give your answer in subscript form. Factorize 24 and give your answer in subscript form. Remember, subscript form is the same as set notation form. So the idea of sets is coming out. That's why in your booklets you find out that many of these are put into the Venn diagram. So you'll be able to answer why this is the only one that is a set. So it's a set that enters the Venn diagram. So we go. Primarize 24 and give your answer in subscript form. Now, I'm going to use a ladder like I did in number 1. We know 24 is one of the multiples of 2. That's why we started with 2 as the first prime number. So 24 divided by 2 get 12. 12 can also be divisible by 2 again. 12 divided by 2 you get 6. 6 is further divisible by 2. That is 6 divided by 2 you get a 3. Then this 3 can no longer be divisible by 2. You got an exponent number 3. Indeed it's a 3, so it can divide itself. So it says 3 divided by 3 you get a 1. In so doing, you have prime factorized. Now the answer is yet to be expressed in subscript form. Now in subscript form, we use the set language. We say factors of 24 as a name to a set. So F24 means factors of 24. Then write equals, open the curly brackets now, and use the subscripts. They look like powers, only that now, for them they will be down. They are called subscripts. When something's up here is called a power, then down is called a subscript. This is the word, subscript. Not sub-biscuit, but subscript. Some will say sub-district. No, it is subscript. So we count on those digits used. So we start 2 the first, 2 the second, 2 the third, and now 3 the first. They are the ones written as subscripts. So factors of 24 equals 2 subscript 1, it's the one there, comma, 2 subscript 2, comma, 2 subscript 3, comma, then 3 subscript 1. So you write these ones here, but as count on them. 2 the first, 2 the second, 2 the third, and 3 the first. So that is the story. But never say 2 the first, but they are read as 2 subscript 1. So 2 subscript 1, 2 subscript 2, 2 subscript 3, then 3 subscript 1. And close in curly brackets. This was called answering in set notation form, also called subscript form. You say factors of 24 are equal to 2 subscript 1, comma, 2 subscript 2, comma, 2 subscript 3, comma, then 3 subscript 1. Before you close the curly brackets, because it's the only one called set notation. The rest must never be put in brackets. Like you see here, there are no brackets. No brackets. The brackets come here and the name with F because of the name of the set. And please put a comma for every member you list, like in the set concepts. You will have answered. Now, that is what's called prime factorization. The question is, if I prime factorize, then what? Prime factorization is useful in many ways in mathematics, some of which are finding the LCM, finding the DCF, finding the square roots, and so many other uses, like we shall see as we proceed. That's why the next subtopic says finding LCM, DCF, and square root, having prime factorized. So that same idea is going to be used here to find the said technical words, LCM, DCF, and square root. LCM in full is lowest common multiple. Lowest common multiple. Lowest common multiple. Then DCF is greatest common factor. Greatest common factor. Sometimes it's called GCD. So where F is, one can put D, GCD, greatest common divisor. Like I was explaining at the beginning, I said factor is a divisor. So that's why we can say GCD, greatest common divisor, instead of DCF. So sometimes it can also be referred to as HCF, highest common factor. HCF, highest common factor, or HCD, highest common divisor. So when you find any of those four, you answer the same way. And then square root, like I was explaining the word square, I said 2 times 2 is the 4. 4 is the square to 2. The 2 is the square root, and the 4 is the square. Like we did understand the other side. Now that we have learned how to prime factorize, we shall note that we use prime factorization to find each of the above. We use prime factorization to find LCM, to find the DCF, and find the square root, like the examples that are ahead suggest. Number 1, find the LCM of 6 and 8. That's the first example. Find the LCM of 6 and 8 using that idea of prime factorization. You are going to use a ladder. Like I told you, we either use a ladder or a prime factor tree. But here, we are using a ladder since we have got more than one numbers to prime factorize. That is 6 and 8. So we draw this table called a ladder, and then we look out for the prime numbers. Remember the first prime number is 2. Can 2 divide any of these? That is 6 and 8. Oh yes, it does for each of them. But I'd asked you for any. But both are in agreement with the divisivity of 2. So both are divisible. 6 is divisible by 2 as well as the 8. So we use 2. It's more than qualifying. So of course 6 divided by 2 you get a 3. And 8 divided by 2 you get a 4. Good. We have got the outcomes are 3 and 4. After dividing by 2, that's 6 and 8. 3 and 4. Now, can 2 work for any of these 2, that's 3 and 4? Yes, it works for 4. Does not work for 3. It works for 4. So if it works with any of the 2, then continuously divide. We say, now 2. 3 divided by 2 doesn't go. If it doesn't go, then it has refused. It goes down as 3. Then 4 divided by 2, you get a 2. So 2. So the outcomes are 3 and 2. Now, since I've got 3 and 2, can 2 still work with any of these? Yes, of course. It works with this solve. So we still write by 2. 3 does not go. It's written down. Then 2 divided by 2 is a 1. Good. Now 2 can no longer work. The next one number after 2 is a 3. Well, of course 3 divides itself. So I've got 2 outcomes of 3 and 1, and 3 divides 3. So that's why I write by 3. 3 divided by 3, you get 1, and 1 divided by 3. Being that 1 doesn't go, it's written down. So the one that's not divisible is written down as a recurring number that has complained about your divisor. So I repeat, with this ladder before we get the answer. We primarize both 6 and 8 on the same ladder. So draw this ladder properly, like the table is, as we go along. So we look at 6 and 8. We are going to primarize, remember. The first prime number is a 2. So can 2 divide any of these 2, 6 and 8? Oh, actually it divides both. So we use that 2. So now 6 divided by 2 get a 3. 8 divided by 2 get a 4. The outcomes are 3 and 4. Now, can 2 still work with any of these? Yes, it works with 4. Doesn't work with 3. So we write a 2. So since it doesn't work with the 3, 3 is written down. It has opposed the divisibility of 2. So then we go 4 divided by 2 get a 2. Good. So now we have got 3 and 2. Can 2 still work with any of these? Yes, it works with that 2. So write that 2. Remember 3 refused long ago. So let the 3 go down and then divide 2 by 2. 2 divided by 2 get 1. Now we've got 3 and 1. Now add 2 cannot still work. The next one number is the 3. Can 3 work with these ones that are here? Yes. It works with the 3 but doesn't work with the 1. So if it doesn't work with the 1, 1 goes down here but works with the 3. Divide. 3 divided by 3 get a 1. So remember, ladder goes up to 1. So whenever you use a ladder, as you know, as you are going up the stairs, or you have a ladder, please you step on the first step. So when you miss a step, you know what happens. So we go 1, 1, and now you have fully prime factorized. Now, what about the second LCM? It's going to be good from these prime numbers that have helped us go up to 1, 1. Now we are going to multiply the prime numbers, that is 2 times 2 times 2 times 3, as they are here. 2 times 2 times 2 times 3, 2 times 2 times 2 times 3. And now we pair here. This is what's called associative property. Pair for easy multiplication. So that we multiply 2 by 2 and get 4, and 2 by 3, you get a 6. So I've got 4 times 6, and which will actually bring that 24. So the LCM of 6 and 8 is 24. Through that idea of prime factorization, we have attained the LCM. We then go to example number 2 that asks us to find the HCF of 20 and 30. Find the highest common factor, which is also greatest common factor, GCF, all HCD and GCD. So any of the 4 terms, please you do like we're going to do. Like I said, HCF or GCF is formed by prime factorization. That's the same idea. So we draw a ladder that is 20 and 30. 20 and 30. Unlike all other ladders, the ladder for HCF or GCF doesn't go up to 1. All the ladders must go up to 1. Apart from that, when you find HCF and GCF, meaning this is an exception. something that doesn't go by the law. Now I've got 20 and 30. Remember, a factor is the same as a divisor. So here they want the greatest common divisor or highest common divisor or highest common factor. So the number you are going to choose here must be a common divisor. That is 20 and 30. And it must be a prime number because you are prime factorizing. So what's the first prime number? Oh, you have answered well. It's a 2. Can 2 divide both 20 and 30? Oh, yes, it's happy. So we divide by 2. Here it's about both, whereas for LCM, it's about n dividing or being divisible by that number. So here, both are both divisible, whereas in LCM, like you saw here, 3 and 4, 3 was not in agreement, but we continuously divided by 2 because 4 agreed. But here, both must agree on the particular divisor you are going to use. So, but it must be a prime number still because you are prime factorizing. So, 20 and 30 are both divisible by 2. Good. If both are in agreement, then you continue and say 20 divided by 2 is a 10 and 30 divided by 2 is a 15. So the outcomes are 10 and 15. Now, the question is, are these two 10 and 15 divisible by 2 again? No, you don't continue with a 2. Remember, you're finding the DCF. It's about agreement of divisibility of the number. The number or the two numbers must agree on that very number dividing them. So like now, 10 and 15 are not both divisible by 2. It's only 10 that is divisible, but the other one is refused. So not both, but one is divisible. But both must agree on the number you are going to use to divide. Now we go to 3. 10 and 15, are they both divisible by 3? No, it's only 1, 15 this time that is in agreement with the divisivity of 3. Then they are not agreeing. Now after 3, we go to the next prime number, which is 5. Now 10 and 15, are they both divisible by 5? Oh, good, we have got you. They are now divisible by 5. So these have agreed to be divisible by 5. So that's why I wrote 5 here. 10 divided by 5 is a 2. And 15 divided by 5 is a 3. Now 2 and 3 don't have any other number. They are in agreement for divisibility. So we leave the ladder like that. We stop there for GCF or HCF. Whereas for LCM and any other thing, we, as soon as we opt for use of the ladder, we must go up to 1. For the DCF, don't go up to 1. No. It's about the common divisor. The number divides both. So 2 divides both 20 and 30. That's why we used it here. That's 10 and 15. Then 10 and 15 are both divisible by 5. That's why 5 is used here. You get 2 times in 10 and 3 times in 15. And now we have another common divisor, meaning you have finished your ladder for the HCF finding of DCF. Now we multiply these numbers that we have used to divide, called prime factors, meaning we have prime factorized. That's 2 times 5, multiply them, thereby getting our HCF as 10. That is how we find HCF using prime factorization. And we shall then look at the last example in this kind of lesson. Thank you for viewing, but continue viewing until teacher says goodbye. So we look at number 3. Find the square root of 36. I said we use prime factorization method or idea to find LCM, GCF, as well as the square root. Now, square root is the one teacher is about to explain. So I've got one number, which is 36. We draw our ladder to prime factorize it, meaning we start with the first prime number. What's the first prime number? Good. You said 2. So now, is 36 divisible by 2? If yes, then continue. Now, 36 divided by 2, you get 18. Is 18C divisible by 2? Yes. You continue. 18 divided by 2, you get 9. Is 9C divisible by 2? No. The next prime number after 2. Oh, you said it well. Say 3. Now, is 9 divisible by 3? Yes. Then you say 9 divided by 3, you get a 3. Then continue. Is 3 divisible by 3? Of course. Now, 3 divided by 3, you get a 1. And now you are fully primary using a ladder. Remember, ladder goes up to 1. Up to 1. Unless 1 is finding the HCF. So apart from the HCF ladder, the rest of the ladders go up to 1. So because you step on the first step as you move on. So we then find the square root. Like here the word square. To square is to multiply a number by itself. So let's first square to get the root. So 2 by 2, please you pair like that. 3 by 3, you pair like this and produce one root of that square. So the root of this square is a 2. The root of that square is a 3. Let this be a 3. Is a 3. So what you have paired is what you pull out. Here pull out a 2. Here pull out 1 3. Because the 1, that's the root cause of the square called square root. So we have got the roots as 2 and 3. They are the ones we are going to multiply and say the square root of 36 is that 2 times 3. We multiply these roots of the square called square roots. Then you say therefore the square root of 36 is the 6. Meaning when 6 is multiplied by itself, that is 6 times 6, you get 36. So that 6 is the square, whereas the square root, the root of the square is that 6. So therefore the square root of 36 is that 6 as you reach perfection. Thank you for following Teacher Katimbo for all that time and sacrificing all that time you have of just following mathematics. Thank you and let God reward you abundantly. For more information about what teacher has explained or he explained before or in mathematics in general, please call this same Teacher Katimbo, this number, MTN line first, 0776 251655. I repeat, 0776 251655. All on Airtel line, which is 07572 33066. I repeat, 075 72 33066. And remember, this work runs all the way from page 78 to 99 of your workbook. Please watch this over and over for you to answer all that work in the said pages of 78 to 99. Otherwise, stay safe.